I read a lot, and while I was reading the other day, I wondered about how many books you could stack to get to outer space, since I figured they were pretty sturdy objects, and it would be cool to just stack books into outer space. In math class, our teacher asked us to try and answer any burning questions we had, so I figured, why not try to answer this one? At first, I thought this would be a pretty easy question to answer. You just need the height of the atmosphere and the width of a bunch of books. Easily Googleable, right? Turns out, I was wrong about that. Finding both numbers required more work than I thought they would. Finding the width of books at first seemed like something I could just Google, but I decided to get more hands-on and measure the width of 400 to 500 books. First wrong decision. After measuring the width of about 50 in the library, I realized this was going to take a while. I ended up measuring just 200 in the library and 200 more at home. The average widths in the library were 1.7 centimeters and the ones at home were 2.1. The average of both is 1.9 centimeters. But then I encountered another problem. The average would not cover all books. I decided to make an inequality representing all the potential widths. I knew that it had to be greater than 0 and less than 32.2 centimeters, since the thickest book in the world has a thickness of around 32.2 centimeters. I came up with an inequality representing all potential widths of books, which was 0 is less than x is less than 32.2, which can also be represented by x is greater than 0 or x is less than 32.2. This would mean that the amount of books would be an inequality and not a definitive number, so it would be easier to find the numbers by graphing. So by now I had two different amounts of required books and needed the height of the atmosphere we wanted to reach. The first source that I looked at, a website that said nasa.gov somewhere in it, said that the atmosphere ended at 100 kilometers. Since it said nasa.gov, I was sure it was a reliable source and used that number to try and find my answer. For the first height of books, I got that you would need 5,263,157.8947 books, or 5,263,158 books when you rounded it up. I wanted to check my sources, so I found another page that said nasa.gov, but this time it was their actual website that showed a diagram of all the layers of the atmosphere and explained each one, which was incredibly useful and where I got my final choice of atmospheric height from. It said that there were 5 levels of atmosphere, and the atmosphere really ended at 10,000 kilometers at the tops of the exosphere, which was the very top level of the atmosphere. I then divided this number by the average width of books to get how many books there were. For my second answer, I got 526,315,789.47 books, or 526,315,790 books when you rounded it up. While looking at this diagram, I was faced with another problem. Would I want to stop when I reached the atmosphere itself, or when I went straight out of the atmosphere? I decided I wanted to go as far as I could, so I aimed for straight out of the atmosphere. The point where the atmosphere started was not that high up, around where airplanes flew through the sky. The lowest level was called the troposphere, and the other levels were called the stratosphere, mesosphere, and thermosphere, each ending and starting at different levels. The exosphere was by far the largest part of the atmosphere and went from 690 kilometers to 10,000 kilometers. So now that I had a new level for the atmosphere, I had to change the number I used for the height of the atmosphere in my equation. I made 2 separate equations this time to show the width of the books and the height of the atmosphere, and look for where they would have crossed over, seeing all the possible amounts of books that could be stacked into the atmosphere to reach past it. Since I wanted to go past the 10,000 kilometer mark, I had to make another inequality for that, making the a variable greater than or equal to 1 billion, since the width of books is measured in centimeters. All I got when adding these numbers into a graph was all the possible widths of books I could use to get to 10,000 kilometers or 1 billion centimeters, which I already knew. I could tell the equation I had was not going to work for this. After arriving to the conclusion that you could not really get a definitive answer for how many books you would need, I realized that there would probably be a range for the amount of books you would need based off of the widths of the books. But I could not find this range. Even with all the numbers and variables I had and all the research I did, I could not solve my question very accurately. The best answer I got was my second answer for my second equation that gave me a definitive number. With the last equation, I would have probably been far more accurate, but I needed more equations that could actually do something to help me solve the problem, because what I had would not help me solve the problem without more advanced math. If you think you know how you can solve this problem, let me know what I could have done to make it work. Thanks!